Hello students, welcome to Vyas Edification Kota. Today we are going to continue with our journey of the chapter on NCERT discussion. We are discussing mathematics class 11th and the chapter which we are dealing with is complex numbers and quadratic equation, and it is time to deal with the very important, the very interesting and the very extraordinary miscellaneous exercise. Let's talk about the miscellaneous exercise without wasting any further time. We'll move to the first question of this miscellaneous exercise. What does the question say? Let's take a look at this. Evaluate this whole complicated expression and simplify this. Let's try to simplify this expression. And do we recall some things related to powers of I? There are some powers of I involved over here, right? What is I? I is square root of minus 1. That is something which we are aware of. And I square is simply equal to minus 1. On the basis of this, we can also say that I power 4 will be equal to squaring this you will be getting 1. So you can remember I square equals minus 1. You can also remember I power 4 equals 1. Okay. So let's try to approach this question. Okay. What do we see? This expression becomes equal to what? This expression can be further written as this is I square power 9, okay, plus 1 over I power 25. This is 1 power 25 upon I power 25 in the square bracket, right? I power 25 can further be broken down into I power 24 into I. Right? I power 24 can be written as I power 24 can be written as I square power 12 times there is another I over here and this whole power 3. That's what we have, right? I square is equal to minus 1, and minus 1 power 9 will be equal to what? Minus 1 power odd number will be a minus. So this will convert to a minus 1 simply. What happens to this I square over here? This I square is also minus 1, and minus 1 raised to power 12, that is an even number, will be actually plus. So this will give me plus 1 over I whole power 3. That's what I obtained. Now what happens to this I in the denominator? We can tackle this I by substituting something for this 1 in terms of I square, that is 1 is equal to minus I square. That is one of the approaches. Another approach could be to multiply the numerator and denominator by I. So in the denominator you will be getting I times I, which will be I square, which is obviously minus 1. In the numerator you will get an I. So this whole thing minus 1 plus, this will be simplified to I over I square by multiplying with I in the numerator as well as denominator power 3, which will further convert to what? This is minus 1, this becomes minus I. That will give me minus 1 minus I power 3. And yes, can you simplify this further? So we'll require something else. What will be required for simplifying this further? We'll require the formula of A plus B power 3. What is the formula for A plus B power 3? This is A power 3 plus 3A square B plus 3AB square plus B power 3. This is the formula for this. So can we use the formula to simplify this expression further? Yes, we can. So let's continue from here. This gives me the first thing that I'll do in this complete thing is I'll take a minus common. The minus power 3 would be actually minus 1 times what will I get in the bracket? I'll get 1 plus I power 3 in the bracket. Is that simple? Yes, it's pretty simple. Once you are through with this, this minus 1 will remain as it is. Do not forget that. And this whole bracket will simplify as A plus B whole power 3, which will convert to A power 3 plus 3 times A square times B plus 3 times A times B square, 3 times A, that is 1 times B square plus B power 3, that is I power 3 will be there, right? Can you simplify that further now? Let's take a look at this. What do we get? There is a minus 1 outside, okay. This is a 1 plus this is 3 times 1 square, which is 3 times I, and I square. What is I square? I square is minus 1. So this is 3 into 1 into minus 1, which will be minus 3. I power 3 can be broken down into I square times I. I square is minus 1 and minus I. Now take the real parts together, the imaginary parts together, and what you will get is 1 minus 3, which is minus 2, 3I minus I, which is 2I. and on simplification this will give me 2 minus 2i, which is my final answer for this question. This is 2 minus 2i, as you can clearly observe over here. And yes, that is all in this question over here. For any two complex numbers z1 and z2, prove that. Real part of z1 z2 equals real part of z1 real part of z2 minus imaginary part of z1 imaginary part of z2. Now how do we go about proving this? So the person is talking about any two complex numbers in general. When the person is talking about any two complex numbers, let's take two general complex numbers. Okay, let us begin with two general complex numbers. What do we begin with? Let us assume that two complex numbers z1 z2 are, let z1 is equal to a plus ib and z2 is equal to c plus id are two complex numbers. Let's say this and this are two complex numbers. Now a, b, c, d can be anything for now, right? A, b, c, d can be any real number. So all complex numbers, for all complex numbers which satisfy this property, this particular result, if we can prove this result for these two complex numbers, then it will be true for any complex number, right? Since a, b, c, d can take any values. Okay, that's what we'll be taking a look at. Let z1 and z2 are two complex numbers. Okay. So in this case, what I'll begin with is I'll try to find the real part of z1, z2, the product of z1, z2, that is important. So let's begin and find the product of z1, z2 first. So therefore, z1, z2 product is actually a plus ib times c plus id. That's simple? Yes, that's pretty simple. Let's multiply them together and apply the distributive law over here. A gets multiplied with c plus id plus ib gets multiplied with c plus id. Okay. Then the a gets multiplied further with c, and this is I times a d plus I times b c plus this is I square times b d. Can you observe that? I times I will become I square and b times d will become this. And this I square can be simplified further. I square is simply equal to minus 1. Now this will be real part, right? This will also be real part. These are imaginary parts. Can we add up the real parts together? Yes. What we'll get is AC. This will become minus BD plus I times AD plus BC. Now I want to comment about the real part of Z1, Z2. Let's talk about real part of Z1, Z2. This particular thing implies that real part of Z1, Z2 is equal to what? This is the real part of Z1, Z2. Can you observe that, right? This is imaginary part, that is real part. This is equal to AC minus BD. Now what is interesting about this AC and BD is A, can you observe here, A is the real part of Z1, yes. C is the real part of Z2, yes. B is the imaginary part of Z1 and D is imaginary Z2. And I'll replace exactly that over there. What I'll do is I'll replace A, this is further equal to, A is equal to, as you can observe, real Z1. C is equal to real Z2 minus B is equal to imaginary Z1 and D is equal to imaginary Z2. Okay. So real part of Z1, Z2 for any two complex numbers is equal to real Z1, real Z2, okay, minus imaginary Z1, imaginary Z2, and this is true for any complex numbers, and this is what we were supposed to prove. And yes, we have proved this particular result over here, right? So for any two complex numbers, we have proved the given identity. That is the final solution for this particular question, as you can see over here, right? Let's discuss this question next. Reduce 1 upon 1 minus 4i minus 2 upon 1 plus I times 3 minus 4i upon 5 plus I to the standard form. Okay, what is the standard form? For any complex number, the standard form is a plus ib form, right? For any complex number, the standard form is z equals a plus ib. Now this is the form which is called standard form. So for converting this complex number into that simplified form and the standard form, what we'll be doing is we'll have to first manipulate this whole thing and simplify this complex number. Let's try to simplify this complex number somehow. How do we go about doing this? Now one of the approaches is to maybe take the LCM over here, but as you can clearly observe, this will complicate things a bit. Another approach which I have in mind is, why not simplify this denominator first, this particular term first, by multiplying with the complex conjugate of the denominator in numerator and denominator both. So let's try to simplify this. Let this whole thing is equal to z. This is 1 upon 1 minus 4i minus 2 over 1 plus I times 3 minus 4i over 5 plus I. These complex numbers in the denominator are creating troubles. Let's try to multiply with the complex conjugate of each term within that term only. Okay, with that term only. Let's try to multiply this. What I'll be getting is, this is 1 plus 4i in the numerator, 1 minus 4i in the denominator multiplied with 1 plus 4i in the denominator. This whole thing can be written as this. Yes. What I've simply done is I've multiplied with 1 plus 4i in the numerator and denominator. What else? This is 2. Let's multiply with 1 minus I, 1 plus I and 1 minus I over here as well. Okay. Once I do this, can I do a similar thing over here also? Yes, I can do a similar thing over here. This is 3 minus 4i, multiply it with 5 minus I, and let's multiply with 5 minus I in the denominator as well. Where did you get that 5 minus I from? It is the complex conjugate of 5 plus I, right? Therefore, I am multiplying with this. What does the simplify do? This is 1 plus 4i, which is okay. What is this? This is 1 square minus 4i square. 4 square I square, which is 16 times I square. 16 times I square would be actually minus of minus 16 plus 16. This will be a 17 in the denominator. Okay. Did we miss anything? No. This is 1 minus 4 square I square, right? 4 square is 16, I square is minus 1, so that will become 1 plus 16, which is 17. Minus 2 times 1 minus I is okay. What will this be? This will be 1 square minus I square, which is 1 minus minus 1, 1 plus 1, which is 2 in the denominator over here. This is what I'll be getting. Yes. Further, what about this whole expression? Let's try to observe this expression over here. What do we get? In the denominator, you get 5 square minus I square. 5 square is 25 minus of I square, which is minus minus 1. That will be plus 1. 25 plus 1 is 26 in the denominator. What about the numerator? So we'll apply the distributive law and multiply 3 with a 5, that is 3 into 5, 15. Minus 3i, okay. Minus 4i into 5 will be minus 20i, and minus 4i into minus I, what will that be? Minus plus 4i square, sorry. Plus 4i square. This is what I'll be getting over here, right? Can we simplify this further? Yes. Okay, this is a 2. Let's cancel these 2's over here. And first, what I'll do is, can I take the LCM over here and between these CS? Let's take the LCM of 17 over here. And what do we get in the denominator is 17. This is 1 plus 4i and minus 17 times this would be minus 17 plus 17i. This is what I'm getting over here. Can you please note that? Yes. This minus goes inside the bracket, the second term becomes positive. Please note that carefully. Take care of the negative sign very carefully. What about this? This is 4i square, which becomes minus 4. 15 minus 4 is actually 11. Okay. And this minus 3 minus 20 becomes minus 23i upon 26. That's what I get in the denominator. As you can simply see, we have two complex numbers getting multiplied in the numerator, and in the denominator we have 17 times 26. We can handle that, right? So this converts to what? What I am getting is 1 minus 17, which is minus 16, plus 17 plus 4 is 21i. Okay. And this gets multiplied with 11 minus 23i over 17 times 26. Right? I hope that's correct. Yes. How do we do it? We simply multiply the numerator in there. Let's do it. So this first term minus 16 will get multiplied with 11. What I'll be getting is minus 16 times 11. Okay. What else? This minus 16 gets multiplied with minus 23i. That will give me plus 16 times 23i. Okay. This 21i gets multiplied with 11. Let's multiply that. Plus 21 into 11i. What else? This 21i gets multiplied with minus 23i, and that will give me minus 21 times 23i square. What about the denominator? In the denominator you have a 17 into 26. Let's multiply that. Can you do it? Yes, obviously multiplication can be done very easily. This is 7, 6, 42, 2, and there's a 4 carry. 6, 7 to 14 is 20, 24. 4 is there and 2 carries. 2 into 1 is 2, 2 plus 2 is 4. This is a 442 in the denominator, right? Can you do a 2 by 2 multiplication very easily? Yes. In a single line? Oh, that is also possible, right? Let's multiply 16 into 11. Now this is simple. 176. This is minus 176. What about 16 times 23? Let's multiply it once again. 3 into 6 is 18. 1 carry. 3, 6 to 12, 13, 14, 15, 1, 6, 16. And then 1 carry. This is 368i. What else? 21 times 11. Now 21 times 11 is again simple. This is 231. 231i. What about the last one? 21 times 23. This is 22 plus 1, 22 minus 1. This is 22 square minus 1 square. 21 is basically 22 minus 1 and 23 is 22 plus 1. So I can multiply them together by converting them in the form a plus b, a minus b. That will be 22 square, which is 484, minus 1, 483. Now minus 483 I square. I square is also minus 1, right? So minus 483 into minus 1 will become plus 483. Denominator you have a 442, and let's add the real terms together, the imaginary terms together. What you get is 483 minus 176. 83 minus 76 is 7. 400 minus 4 minus 1 is 3. This is 307. And what else? What do you have over here is 599. 599i. Right? This is 599i upon 442 in the denominator. And is that all? Yes, that is all. Is it in the form a plus ib? We can write it in the form a plus ib by taking this 442 with each term, right? This 442 goes here and this 442 goes here. This is the final answer. This in the standard form is what we have done. 307 plus 599i upon 442. That's the complete solution of this question over here. Question 4th. If x minus iy is equal to square root of this complicated expression a minus ib upon c minus id, prove that this x square plus y square whole square is equal to a square plus b square over c square plus d square. This is equal to this. Now how do we go about proving this? Okay, let's take a look at this. Now I'll discuss two methods with you. Two methods, yes, let's discuss two methods. One is the smarter way. Let's do it with the smarter way first. Another is a longer way. Probably you would have seen that somewhere maybe, but let's do it with a smarter way first. What I'll do is, we're given that x minus iy is equal to square root of a minus ib over c minus id. Now what I observe over here is, this is a square b plus b square, this is c square plus d square. It has got something to do with this numerator and this denominator over here, right? And x square plus y square whole square is also present. So x square plus y square has something got to do with this. Basically it is x square plus y square is nothing but modulus square of x minus iy, right? If x minus iy is a complex number, we take its modulus. What we will get? Under root of x square plus y square, yes. So we'll go in that direction only, but first let's remove this square root from here and let's write it as this. A minus ib over c minus id. This is what you have, right? And once I reach this stage, there are two complex numbers on both sides, LHS and the RHS. What I'll do is I'll take modulus both sides. So what I'll do is, since this is equal to this, their modulus would also be equal. So take modulus both sides. And what does it give us? This gives me modulus of x minus iy whole square can be moved outside the modulus, shifted outside the modulus, and this can be written as a minus ib upon c minus id modulus. Okay, so for the time being you can also write it as, let us say, x minus iy square and modulus. Now let us apply the properties of modulus and convert this further into this is x minus iy modulus square is equal to, this is modulus of z1 upon modulus of z2, which can be written as mod z1 upon mod z2 upon mod of c minus id. Now what is modulus of x minus iy? Let's try to find that. Modulus of x minus iy is under root of x square plus y square. Okay, and yes, there is a square over there. Okay, what happens over here is, this is a minus ib modulus. What is the modulus of a minus ib? That is under root of a square plus b square. What is the modulus of c minus id? That is c square plus d square in the denominator. Okay, this is under root on the right hand side. Why not square both sides? We can square, but let's first square within this. What you get is x square plus y square equals under root of a square plus b square by c square plus d square, and you may now observe getting the final result in a single shot, that is squaring both sides. You will get x square plus y square whole square is equal to a square plus b square over c square plus d square. And is that what you wanted to prove? Yes, we wanted to prove this only. So given, with the given condition, we have reached the equation which we wanted to prove. We have reached this stage with the given condition by a series of manipulative steps, that is taking modulus and all, and that is giving us the final proof over here, right? But you talked about two methods, right? There's another method, there's another approach which we can follow over here. Should we discuss that? Yes, let's discuss that. X minus iy is equal to a minus ib over c minus id. What you will do is, you will square both sides first. Okay, there's another method. The other method I'm discussing now. Instead of taking modulus both sides, what you will do is, you will simplify this. Now how do we simplify this? I'll write a few steps to give you a glimpse. Let me write a few steps. A few steps, yes, just a few steps, because the solution will be pretty long in that case. Let me just write the square. This is x minus iy whole square. What will that convert to? This is x square. This I square y square, that will become minus y square, and minus 2xyi is equal to, we'll have to multiply with complex conjugate of c minus id in the numerator denominator. This is a minus ib c plus id over, this is c square plus d square in the denominator. Okay, multiply the terms on the RHS, simplify them and compare the real parts. First compare the real parts together. Real parts, x square minus y square would be equal to something, 2xy would be equal to something, yes. And on the basis of that, try to find this expression. Now what is this expression? This is x square plus y square whole square. So first we'll have to find x square plus y square, right, with the help of that. Now that will take a long time and it will be pretty, the steps would be many, there would be chances of silly mistakes, but then this is another approach which you can follow and to get the final result, that is this. Pretty long? Yes, pretty long. The first one is pretty simple and that is something which you can follow. I've just explained that first method and that is pretty simple, which you can follow very easily, right? That is all in this question. Let's talk about this one. Convert the following in polar form. There are two parts of this question, 1 plus 7i upon 2 minus I whole square. What do you mean by polar form? Polar form of any complex number. You may recall, polar form of any complex number z is r cos theta plus I sin theta, where r is actually the modulus of z and theta is actually the argument of z, represented as this argz, and theta belongs to minus pi comma pi in this interval, right? Principal value of the argument lies in this particular interval. That's what we are aware of, right? Now let's try to attempt the first part and the second part. First we'll have to simplify them, right? First we have to simplify them because converting in this form is easy from the Cartesian form. Now what is the Cartesian form? There is a Cartesian form also. What is the Cartesian form? Cartesian form is z equal to x plus I y. And for converting from here to here, we remember that x equals r cos theta, y equals r sin theta. This is there. This can be observed by plotting the point in the Argand plane very easily. Let's say there is any point P. Its location can be represented by x comma y, or it can also be represented by r comma theta in terms of polar coordinates. This is 90 degree, this distance, this length, this particular length would be x, this would be y, and this here would be r, this angle would be theta. So for reaching point P, what you can do is you can move along the real axis a distance x and along the imaginary axis a distance y, you will reach P. Or you could move in another direction at an angle theta with the positive axis. You can move a distance r along that ray. Okay. In both cases, you will reach the point P. Yes. And the relation between this is this simple relation, right? Okay. So with this in mind, let's try to first simplify that whole thing in the Cartesian form, which is very easy. Right? Let's try to do it. First part. Z equals 1 plus 7i over 2 minus I whole square. Okay. Now in the denominator you have 2 minus I whole square. We'll have to simplify that first. Let's do it. This is 1 plus 7i in the numerator. This is 2 square, which is 4, plus I square. I square is minus 1 and minus 4i in the denominator. What will that give me? This is 3 minus 4i in the denominator. There is 1 plus 7i in the numerator. Okay. For simplifying this further, we'll have to multiply with the complex conjugate of this 3 minus 4i. Let's do it. Where will this take us? You can multiply these two terms together. This is 1 into 3 is 3. 1 times 4i is plus 4i. This is 7 times 3 is 21i. And 7 times 4 is 28 I square. What about the denominator? In the denominator you have a minus b, a plus b. What you will do is a square minus b square, which is a square is actually 9. We can directly write 9. 3 square is 9 minus 16 I square. That's what you observe, right? 4i whole square would be 16 I square. Now I square is also equal to minus 1. You may recall that. This is minus 28. 3 minus 28 would be minus 25, right? Yes. 4 plus 21 is plus 25i, and this is 9 plus 16 in the denominator, which will further convert to what? Can you observe that you can take a 25 out from the numerator? Minus 1 plus I will remain, and you have a 25 in the denominator as well, which will get cancelled, implies z is actually equal to minus 1 plus I. Now, that's the first stage that we reach on simplification. Now once we have reached this stage of simplification of z, we'll have to convert this now in the polar form. We'll have to convert this simplified z in the polar form. This is the polar form. How do we do that? How do we do that? This here minus 1 plus I is the complex number which is there in the Cartesian form. Now x is equal to r cos theta, y is equal to r sin theta. So let r cos theta is equal to x. X is minus 1, you can clearly observe over there. This is a real part, and r sin theta is equal to 1. On squaring and adding, therefore r can be easily obtained. R can be easily obtained by simply, as you can clearly observe, r can be easily obtained by squaring and adding these terms. R square cos square theta, r square sin square theta. Add them together. What you get is r square, which is minus 1 square plus 1 square. Right? Let's do that. This is under root of minus 1 square 1 plus 1, which gives me r is equal to root 2. R comes out to be square root of 2. Once we have found r, the next thing that we are supposed to do is find theta. Okay, how do we find theta? We'll find theta, but let me get rid of this particular portion over here. this particular portion over here, right? You're solving the first part, yes, first part continued. From here, we'll move there, okay? So once we have r, therefore cos theta is equal to minus 1 upon r, which is minus 1 by root 2, and sin theta is equal to 1 over root 2, as you can observe over here. Sin theta is positive, cos theta is negative, means theta lies in the second quadrant. Theta lies in the second quadrant, and seeing the angles, can you observe that? Seeing the angles, you can observe theta lies in this quadrant, and this particular angle over here is supposed to be, seeing the angles, you can observe this is pi by 4. But theta, as you all know, is measured from the positive x-axis in this direction. So theta would be pi minus pi by 4. Theta would be pi minus pi by 4, which is 3 pi by 4, and therefore z, that is the complex number finally converted in the polar form, would look like root 2 r times cos theta plus I sin theta, which is cos of 3 pi by 4 plus I sin 3 pi by 4. This is what the first part will look like in the polar form. Z equals root 2 cos 3 pi by 4 plus I sin 3 pi by 4, and yes, this is my final answer. Complete solution you have already seen. This is my final answer for this first part. This is the final answer for this first part. And without wasting any further time, what we'll do is we'll solve the second part as well. Let's solve the second part now. Same ideas of conversion will be applied. First, we'll simplify the second part. Let's do it. Let z equals 1 plus 3i over 1 minus 2i. What we'll do is we'll multiply with the complex conjugate of denominator in both numerator and denominator. On multiplying, what you get in the numerator is 1 plus 2i plus 3i plus 6i square. This is what you get in the numerator. Denominator will be giving me 1 square minus 2i whole square, which is minus 4i square. This will give me minus 6 plus 1 would be minus 5 plus 5i whole divided by, this is 1 plus 4. This will convert to, let's take a 5 common from here, minus 1 plus I over 5, and on cancelling these I get minus 1 plus I. Oh wow! The z that we obtained in the first part and the z that we obtained in the second part are exactly same. They've just been written differently. Represented differently, but they are actually the same z, and for this z also r would be equal to square root of minus 1 square plus 1 square, which is square root of 2. Okay, and r cos theta equals minus 1, r sin theta equals 1 implies r cos theta is x, that is minus 1, r sin theta is y, which is 1, implies cos theta is minus 1 by root 2, sin theta is 1 by root 2. That's what you can observe, yes. Cos theta is this, sin theta is this, implying theta is pi minus pi by 4, or you can say this is 3 pi by 4. Once you are aware of this much, then we can simply write, therefore, z equals root 2 cos 3 pi by 4 plus I sin 3 pi by 4, which is my final polar form of this complex number as asked in the given question. This is all? Yes, this is all in this question over here. Solve each of the equation in exercises 6 to 9. Now we'll be discussing the sixth one, and what we have over here, you have to solve for the value of x, and this is a quadratic equation in terms of x. Okay, let's try to approach this question. This is a quadratic equation, and quadratic equation can be solved with the help of simple quadratic formula, right? What does the quadratic formula say? The quadratic formula for ax square plus bx plus c equals 0 when a is non-zero. When a is non-zero, x becomes equal to minus b plus minus the square root of b square minus 4ac over 2a. This is the value of x. That's the solution, right? This is the Sridharacharya formula for solving the quadratic equation, in which this b square minus 4ac is called discriminant or represented by d, capital D. Depending upon the values of capital D, whether positive, negative or equal to 0, we can comment upon the nature of roots of this particular equation, right? Now what do we have over here? We're simply supposed to solve, right? Let's try to solve this. For example, this quadratic equation, let us compare this quadratic equation with the given quadratic equation, and therefore for this quadratic equation what we have is a equals 3, b equals minus 4 and c is equal to 20 by 3. b is minus 4 and c is 20 by 3. Therefore, capital D, which is b square minus 4ac, can be found easily. What is b square minus 4ac equal to? Let's take a look at this. This is minus 4 square, which is 16, minus 4 times a times c. And you can clearly observe this 3 and 3 gets cancelled. This is 16 minus 80, which is minus 64. Pretty interesting. D is minus 64, D is negative. Okay. Therefore, x equals minus b, as you can observe, minus b, which will become plus 4, plus minus under root of minus 64 upon 2 times a. A is 3. That's what you observe, right? Now, root of minus 64 can be written as root 64 into root minus 1. Now, square root of minus 1 is simply I, and yes, this will convert to 4 plus minus root 64 I upon this is 6. Okay, let's try to simplify this further. This is 4 is okay, plus minus this is 8I over 6. This is plus or minus over here, right? And further we can cancel a factor of 2 and get 2 plus minus 4I over 3. This is my final answer for this question over here. This is the final answer for this question. Using the Sridharacharya formula, we have solved this quadratic equation and obtained this answer. 7th, we have a quadratic equation once again. Let's try to solve this quadratic equation. In the formula for ax square plus bx plus c equals 0, what do we have? A equals 1, b equals minus 2, c equals 3 by 2. Okay. And d equals b square minus 4ac, which is equal to minus 2 square minus 4 into a into c. C is 3 by 2. What is this? This is 4 minus what is 12 by 2? 6, which is minus 2. The value of d is minus 2. Therefore, x equals minus b plus minus under root of b square minus 4ac upon 2a. Sridharacharya formula, yes. What you obtain is minus b, which is minus or minus 2, that will give me 2 plus or minus under root of b square minus 4ac, which is minus 2 over 2 times a is 1. What will this give me? This is 2 plus or minus root of 2 times I over 2 over 2. Right? This is what I get. And yes, those are the final values of x that I want. Is that my answer? Yes, that is my answer for this question over here. Right? Let's take a look at this one. 27 times x square minus 10x plus 1. We are supposed to solve for x. We are supposed to solve for x. Can we? Yes, we can easily solve for the values of x. Let's try to do that over here. A equals 27. B equals minus 10. C equals 1. A is 27. B is minus 10, C is 1, and D, that is the discriminant, is b square minus 4ac in this equation, and what you get is b square, which is minus 10 square, which is 100, minus 4 into 27 into 1, 4 into a into c. This is 100 minus, what is this, 108. This will be minus 8. Okay, discriminant is negative. Okay. Since x is equal to what? X is equal to minus b plus minus under root of b square minus 4ac over 2a implies x equals, What is minus b? Minus b would be minus 10, which is 10, plus or minus square root of d, which is minus 8 upon 2a. Now 2 times 27. Okay, 10 is okay. Plus or minus, this is root 8 times root of minus 1, which is I, upon this is 54. 10 is okay. Plus minus, this is 2 root 2. Root 8 can be further broken down into 2 root 2. I upon 54, and you can observe that there is a factor of 2 which is getting cancelled in the numerator and denominator. This will give me 5 plus minus root 2 I over 27. This is my answer for this question. Let's take a look at this one. 21x square minus 28x plus 10 equals 0. What do we begin with? We begin with the values of a, b and c, as you can observe over here. The values of a, b and c, as you can observe over here, would be a equals 21, b equals minus 28, c equals 10. These are the values of a, b and c, and d will be equal to b square minus 4ac, which is equal to what? That is, b square is minus of 28 ka whole square. What is that? Minus 28 whole square. 28 square is 784. Let us confirm that. This 8 square is 64, 6 to 16 to 32, and 6 would be 8, 38, and 2 into 2, 784 is okay. Minus 4 into a is 21 times c, which is 10. Okay, that's what we have. This is 784 minus, what you get over is 840. Let's subtract them together, and this is 56 minus 56 over here. That's what we obtain. Let's use the Sridharacharya formula now. Minus b plus minus square root of b square minus 4ac over 2a. Since x is equal to this, therefore minus of b would imply minus of minus 28. This is 28 plus minus under root of b square. What is that? B square minus 4ac is completely solved and found to be minus 56 over 2 times a, which is 2 times 21 in the denominator. Right? Now root 56 can be simplified further. Root of minus 56 can be written as root 56 times root minus 1. First of all, let's do that. This is 28 plus minus root 56 times root minus 1, this, and this is a 42 in the denominator. Now what does 56 have? 56 is actually equal to 7 times 8. Okay, 8 has a 2 square in it, so 2 can come out from there, and what you get is 28 plus or minus 2 root 14i upon 42. Let's cancel that factor of 2 in the numerator and denominator. X equals 14 plus minus root 14i whole divided by 21. That's what we have as answer. Finally, 14 plus minus root 14i upon 21. This is the answer for this question over here. Let's talk about this question. If z1 equals 2 minus I, z2 equals 1 plus I, find modulus of z1 plus z2 plus 1 over z1 minus z2 plus 1. Okay. Now what are we supposed to do in this case? We have to find the modulus of this big number, but then that number can be simplified, right? Let's do it. Let's try to simplify this. What do we have over here? Modulus of z1 plus z2 plus 1 over z1 minus z2 plus 1 equals what? This expression will be equal to modulus of, let's substitute z1. Let's substitute z1. z1 is 2 minus I plus z2 is 1 plus I plus 1 is extra. Okay. What about the denominator? In the denominator you have 2 minus I and you have minus z2, which will be minus 1 minus I, and you have a plus 1 in the denominator as well. This is what you get in the denominator. Yes. Okay. Let's add the real parts together in the numerator. 2, 1, 1, that is 4. Minus I plus I is gone, that will give me a 4 in the numerator. What about the denominator? In the denominator I have 2 minus 1 plus 1, which is 2, minus I, which is 2 minus 2i in the denominator. This is what I get in the denominator. Okay. I can cancel this factor of 2 and I'll get 2 times 2 upon 1 minus I modulus. Now modulus of Z1 upon Z2 is equal to modulus of 2 over modulus of 1 minus I. Modulus of 2 is simple, that is 2 only. 1 minus I modulus is under root of 1 plus 1, which is square root of 2, simplifying to square root of 2 finally, and yes, that is my final answer for this question, as you can observe clearly, right?